Yeah, dear, this is Kanpur and winter season. We are recording in extreme cold. In Hindi we say halat kharab hai. We are talking about controlling an aircraft. I wish I knew how to control this temperature. Doesn't matter, interacting with you gives me enough warmth and that makes me continue with recording. So let's go back. We have been discussing about controlling the aircraft. And if you recall, in your previous lecture you have seen what do you mean by controlling an aircraft is suppose this is Cm and let's say this is Cl or alpha, whatever way you plot, and you know that this slope is dCm by dCl or dCm by d alpha. Depending upon in x-axis you are putting Cl or alpha. What is our aim? Our aim is to trim the airplane at this point, which is called trim point. What is the meaning of trim point? Suppose the airplane needs to be flown at a cruise. The cruise means the airplane is, if I draw the airplane here, so it should generate enough lift to balance the weight and enough thrust to balance the drag. So if this corresponds to a particular CL, then I must ensure half rho V square SCL equal to W. So that will give you, for a given W, given decided speed, given altitude sir rho, and given wing area, that will tell you what is the CL I should fly. That means what is the CL at which I will trim the airplane. That further means that what is that CL I will be flying such that there is no pitching moment. It is Cm equal to 0. Okay, it's flying like this. And this is one of the equilibrium state, and we have understood the slope is negative, dCm by dCl is negative, or dCm by d alpha is negative. Accordingly, you have decided to put Cl or alpha here, and you know that if by some disturbance the angle of attack increases here, if I talk about angle of attack to be this axis, if angle of attack increases here, then it will automatically generate negative pitching moment, okay? Because this Cm here is negative, here is positive, it will automatically generate negative pitching moment, which will try to take alpha back to the trim alpha. And that is why we say it has an initial tendency to come back to the equilibrium. So it is statically stable. So two things, one is dCm by dCl should be negative, or dCm by d alpha should be negative, and to trim at positive angle of attack, generally you should ensure that Cm at alpha equal to 0, right, or Cm at Cl equal to 0. Since I am more discussing with alpha, Cm at alpha equal to 0, which is denoted as Cm naught, it should be positive. Generally, that is the configuration with which you want to fly. Now, what is control? What we discussed was, suppose I want to trim the airplane at a different alpha. So the moment I try to take the airplane from this angle of attack to another higher angle of attack and still maintain lift equal to weight and thrust equal to drag, what will happen that this gentleman, because it is statically stable, it will generate a negative moment. It will not allow it to go to that new Cl or alpha. So you have to forcibly nullify that, and that is where you give a delta E deflection in a manner that it generates a positive pitching moment and nullifies this negative pitching moment, and you can draw the line to be something like this. That is what is the control part. I am talking about elevator only. Same thing will be true for a rudder and aileron, you will see when the lecture progresses. And to formulate that, we have seen that what is that delta E required to trim an airplane at a particular CL trim. So we say it is delta E naught plus d delta E by, or here I write d delta E by dCl into CL trim, and where d delta E by dCl is nothing but minus dCm by dCl by Cm delta E with some approximations when we put. Okay? This is the neat and clean linear expression. Now, what is the meaning of this? Meaning of this is that when I decide I need to trim at a particular CL, I need to know what is the value of d delta I by dCl. Who decides that? That is decided by dCm by dCl, and you know dCm by dCl has a relationship with static margin. If static margin is large negative or static margin is large, that means dCm by dCl is more negative. Okay? And also you need to know how effective is Cm delta E, what is the control power. It is very obvious that if dCm by dCl is very, very large, that is highly stable, then this value will be very, very large, so delta E required will be very, very large, which confirms to our understanding that if an aircraft is highly stable, so it is very extremely difficult to take it from one trim to another trim for simple reason, because highly statically stable, it will oppose it. So that is why this dCm by dCl is a priori designed in such a manner that all these deflections are physically possible, either through pilot, directly through pilot, or all the older aircraft, smaller aircraft, or through actuators and boosters, right? This is the understanding. But what in a nutshell, what we understand is from this discussion and a previous lecture that there is a unique value of delta E required for a given CL trim, given your delta E naught value and d delta E by dCl values, right? And you by now know that delta E naught is also related to Cm naught, which is a characteristic of the airplane, how you have laid the tail, how you laid the wing, and d delta E by dCl is nothing but they are related to static margin, dCm by dCl, and the control power. So what is the understanding? If I want to trim at a particular CL, which is CL trim, I have a unique value given these things, which will not change. Once the airplane is flying, we assume that the derivatives are not changing with speed. I am talking about low speed, and also CG variations are negligible. So all the things remain constant. So I need to know a priori that delta E required, which is unique value for a given CL trim. Okay, so what is the meaning of that? Suppose this is your elevator. I start measuring from here. For a particular CL trim, I need to go to, let's say, 3 degrees. For another CL trim, I need to go to 5 degrees, like that. These are fixed, depending upon value of d delta E by dCl, delta E naught, and CL trim. Correct? So whatever we have talked in terms of stick fixed stability so far, it assumes that here I start from here and I put it here, lock it, nothing to move. It will not be allowed to float. It will not be allowed to float. This is a new word I am now adding because I want to come to a new topic now. What is this meaning of float? Let us see. But remember, there for a particular CL trim, you need a unique value of delta E required. Right? How do you go it? How do you achieve that delta E? That is the matter I am going to discuss now. In one case, for a stick fixed case, I am saying it was delta is like this, I need 5 degrees, take it to 5, hold it. I am not allowing any floating of the elevator. What is that floating of the elevator? That is exactly where we will be discussing now. Let us have a closer look on the tail. This is the horizontal tail. Since I am talking about longitudinal stability, I am mostly talking about horizontal tail. And let's say this tail is seeing some angle alpha t, alpha tail. And as you know, these elevators are hinged through a hinge line, and they are free to rotate about the hinge line. Okay? You have become enough aerodynamists to understand that the moment there is an alpha t angle of attack, it also sees alpha t. So there will be some pressure distribution across this elevator also. And that also will have some sort of a center of pressure. And if the center of pressure is behind the hinge line, what will happen? The force will act like this, and this will give a moment like this. So this elevator will try to float. We say elevator is floating. That is, for a particular alpha t, the elevator by itself will float as long as the overall center of pressure of the elevator is behind the hinge line, which is mostly the cases, right? So if I want to model that, how do I model? And why do I model? Because I told you delta E required is a fixed unique number. In first case, stick fixed case, what we did, we said, okay, if it requires 5 degree, I don't care whether it float or not, I will not allow it to float, I'll simply take elevator from 0 to 5 and hold it. I will not allow it to float, because if I allow it to float, now it will get some other angle. That is why stick fixed, okay? So this is very important, that elevator will have a tendency to float. What does this float means? Let us understand this. I am focusing here. I call there is something hinge moment, HM, which is hinge moment. I model this hinge moment as I am modeling pitching moment, I write it as half rho v square at tail into S elevator, C elevator into CH, which is the hinge moment coefficient. Is this clear? I am defining hinge moment as half rho v square at tail, S elevator, C elevator, and CH is the hinge moment coefficient. Like we have pitching moment coefficient as Cm, right? What is C? C, we have defined it like this. If this is the elevator and this is the hinge line, then from hinge line to the trailing edge, this is defined as CE, elevator chord. This is the elevator chord. Please note that by convention, we are defining it from the hinge line to trailing edge of the elevator. And AC is obvious, the area of the elevator. Correct? If this is true, then what is happening, let us see. We need to know how CH will vary. CH will be function of alpha tail, obviously. CH will be also function of elevator deflection, because that will generate a different pressure distribution over the elevator. And CH also will be function of delta T if there are some tabs. I will discuss about tabs if time permits. If this is the elevator, and there are some tabs here also which can float, can be set down or up, and this is these are for trimming, final trimming, and also that we will see that will reduce the hinge moment effort for the pilot. We'll discuss about tabs. But at present, to understand the physics, we'll say there are no tabs. Note down this, and we'll come back to tabs. Once you understand this simplistic formulation, adding tab effect will be just trivial. Okay? So this CH is function of tail angle of attack and elevate. This we must understand, and we will do a simplification which may not be true always. We'll assume that CH can be expanded as a linear combination of alpha T and delta E, where we're actually essentially assuming that whole effect is linear. In practice, you'll find it may not be linear, but for our understanding, we are doing this simplification. And in fact, a lot of efforts are put in wind tunnel testing to get actual value of hinge moment coefficient. Okay? Now, why all this? Before I go deep into it, let us understand there are two types of control you will find. One is reversible, and there is irreversible. What is the meaning of reversible control? I write control here so that you remember. This is also control. What is reversible control? Now suppose this is the elevator, right? And there is a stick in the cockpit. If I move the stick, then the elevator will move up or down depending upon how it is designed. Similarly, if I move elevator up and down, the stick also will move forward or backward, right? Generally, the one convention is followed. If I am pushing the stick, right? So I am trying to accelerate the speed, so I need lesser CL to trim for the same weight, okay? So if I am pushing the stick and I am increasing the speed, so I need lesser CL, so angular of attack has to be reduced, so you will see the elevator will go down. And reverse, it will go up. But for a reversible, if I move the elevator, the stick also will move. So they are linked directly like that. However, for an irreversible control, there are boosters, right? So if I move the stick, elevator will move, but if you move the elevator, stick will not move, right? So next part of my lecture, whatever we'll be doing, we'll be discussing, mostly focused on reversible control, not irreversible control. And that is how we will be developing a model. What is the nature of stick force the pilot has to apply for flying the machine? One thing is very clear. For a particular CL trim, he has to have a definite and unique delta E value, delta E required value. That's no debate on that. But when he is flying, if he is flying with a stick for a reversible control airplane like all small aircraft, even nowadays that also is becoming irreversible, we are trying to model how much stick force he has to apply for a per unit deflection of elevator. Or if you want to change the speed, how much stick force he has to apply. That is important to understand one thing, that the handling qualities of the airplane. So you cannot design an airplane where pilot has to put all of his weight to pull the elevator or push the elevator, okay, right? So from that angle, there is a concept, mostly books are not mentioning that, but we will be talking about in some perspective. It's called stick free stability. I repeat, so far previous to this lecture, everything was focused with the concept of stick fixed. We are not allowing the elevator to float. Whatever 5 degree, then we lock it. So it cannot float. But you know, if I leave the elevator free, then it will have natural tendency to float. How much it should float, how much it will float, can I model it or not? That is what we are now attempting. Okay? By simple common sense, you understand that this elevator for a given alpha t will float till that time when the hinge moment coefficient becomes 0. Naturally, till there is a hinge moment coefficient is there, it will go on floating. So what is that? Delta E float. It's delta E float corresponds to when the CH becomes 0. And what is CH? How do I model CH? As I told you, we'll assume that it is behavior is linear. Right? Then I write CH as CH naught plus CH alpha t into alpha t plus CH delta E into delta E. Let us not forget one thing. What is CH alpha t? These are a partial derivative. That is delta CH. What is CH alpha t? Please understand this concept once for all. Nothing but delta CH by d alpha t. That means it is a change in hinge moment coefficient for a change in alpha t, keeping other constants. So these are partial derivatives. Similarly, CH delta E is delta CH by delta delta E, keeping alpha t constant. So it is typically a partial derivative in concept, and typically we are using the advantage of the assumption that it is linear. Okay. We will further assume that CH naught is 0. Let's say the aerofoil is symmetric and the construction is very symmetrically made, but in practice you will find even if you put symmetric aerofoil, the construction will have some sort of asymmetry. So CH naught in fact will not be 0, a small number. But for our purpose, CH naught we are assuming 0, because if there is a CH naught value, you have to only add the mathematics, which is as simple as that. So nothing new physics you will get out of it. So to have the physics clear, we are adding CH equal to CH alpha t into alpha t plus CH delta E into delta E. One of my requests to all of you, I will be writing this equation. Every time I will try to give a physical meaning of those things, you should have a pen, pencil, and a notebook with you, and you should do it yourself. Okay? So now see, delta E float is what? How do I find out? We have understood by applying our common sense that delta E elevator will float till that time when CH is 0. So now I put CH equal to 0 here. So 0 equal to CH alpha t into alpha t plus CH delta E into delta E. I write here float. So what is delta E float? Delta E float is nothing but minus CH alpha t by CH delta E into alpha t. Very important relation. How your mind get excited now? See, whether delta E float will be up or down, who decides that? Let's say alpha t is positive. For a positive alpha t, whether delta E, that is the elevator will go up, float up or float down, who will be deciding that? That will be decided by this sign of CH alpha t, CH delta E along with minus here. If this number comes minus, that means it will float up. If this total number comes plus, it will go down for a positive alpha t. Let us see what is CH alpha t and CH delta E as per their signs are concerned. As initially I told you, if this is the elevator and this is the hinge line, and because of pressure distribution, generally center of pressure will be behind the hinge line, or hinge line is adjusted. Most of the airplanes, it is ahead of the center of pressure over the elevator. So naturally you could see for any alpha t, it will give a moment in this direction. So CH alpha t will give a nose down moment. So it is negative, right? Similar thing happens, you could see because of delta E also. If there is a delta E deflection, again, force will be like this, which will again give nose down moment. So we could see as long as hinge line is ahead of the center of pressure of the elevator, right? So CH alpha t and CH delta E are less than 0. This is very, very important. Okay? Now, if they are less than 0, then this is negative, and this is negative term here. So for a positive alpha t, if it is positive, what do you get? It implies delta E float will be negative. That means it will float up. Is it clear? And most of the airplane, this is what the tendency. So what is the message you got? Most of the airplane where the hinge line is far ahead, the center of pressure of the elevator, or let's say aerodynamic center of the elevator, which are almost same for a symmetric aerofoil, for a positive alpha t, the elevator will try to float upward. Okay? This is first, mathematically. Second is what? Second is, suppose you want to take the elevator to 5 degree. One is take fixed case, take 5 degree, hold it. But if you are talking about hands off, that is, I will lift the stick and it will really go to 5 degree, then you have to be very careful. You know that at 5 degree, if I leave it, then because of alpha t at 5 degree, the elevator will float further up. So it will not be 5 degree, it will be more than 5 degree. Okay? This is one essence. Second thing, if the pilot has to put his stick, and so the stick force, the elevator will turn like this. So one should be smart enough to know that pilot should put that much of effort to take it to that much of difference in angle, because already by elevator by itself will float by some degrees. So pilot should put effort only for the remaining angle. Let's say 5 degree is the aiming angle for elevator, and by float it is going to 3 degrees. So pilot effort will be only for 2 degrees. Okay? Because anyway it will float. But the only problem comes in modeling is this floating angle changes at different alpha t. So it becomes really complicated. Okay? But in a nutshell, you understand that since it is floating up, we must know how much it will float, and we should try to use this concept to define a mathematical model which will relate stick force and CL trim for a reversible control, right? That is the catchword, reversible control. Because for irreversible control, there are boosters in between, so the pilot force and actual deflection relationship is overridden by the actuators and the boosters. So you cannot give a direct feel. Of course, artificially they are simulated, but that is not our purpose. So this is a delta E float. Thank you very much.